1.10 is dealing with elementary matrices and matrix inverses. So as we begin this section, let's begin refreshing what our three elementary row operations are. The first one is that we can take a row and we can change that row by multiplying it by some scalar, some constant. For example, if our pivot that we're trying to change into a 1 is a 3, then we can change that by multiplying that row by 1/3. Our second operation, if we need to add two rows together, we can create our new row by taking that row and adding or subtracting another row multiplied by some constant. Now, one thing to be careful here is that the row that we're trying to get, when we take its previous row, notice it doesn't have anything multiplied by out front. What's being multiplied by something is another row that we're using to get that row. So notice the row that has the number multiplied by it is not the same row that we're changing. For example, if I had some matrix and I was trying to get a 1 right here, which I would have a different number there, I guess. Let's say we have a 1, a 2, a 2, and a 3. If I was trying to use this number to get a 0 right here, not a 1, a 0, then I wouldn't multiply this row by something. My second row would come from using this 1 and making it a -2. So I'll do -2 times that first row plus the second row. Notice the second row I'm not multiplying by any constant. Now to give us our 0 here. So that's just a little subtlety. We've kind of overlooked some in the past, but we do need to be careful with that. In our third operation is we can swap two rows in our matrix if we wish. So we're going to define an elementary matrix to be a matrix that when we multiply it by another matrix causes an elementary operation. And it's just going to be an offshoot of an identity matrix. So let's deal with a 3x3 matrix. The identity 3x3 matrix has 3 rows, 3 columns, and has 1s on the diagonal. So let's suppose we have another matrix and we need to get our new second row, we need to take the first row, the previous first row, times 2, and add that to our previous second row. So the way we write an elementary matrix to perform this is in the second row of our identity matrix, that's the only one that's going to be changed. So the first row and the third row are the same. In the second row, we're going to use these numbers as our coefficients. So in the row 1 place, we're going to use a 2. In the row 2 place, we're going to use a 1. There are no 3's in here, so 0. So when we take a matrix and multiply by this matrix, it's going to have this effect. It's going to double the first row and add it to the second row. So let's illustrate that with an example. One thing. So what we need to do, let's come up with a matrix. just going to make one up, and it might not necessarily be putting something in row echelon form. But let's suppose we have a matrix 1, 1, 1, 2, 2, 2, 3, 3, 3. And let's multiply it by this elementary matrix. Now, one key here is that when we multiply by an elementary matrix, it has to be on the left side. If we put this matrix on the right side and multiply by it, while our rows and columns do match up, it will not perform the elementary row operation that we desire. So let me shrink this real quickly, get that out of the way. All right, now let's multiply these out. Now remember, we do a row times a column. So notice, since there's just a 1 here, that's only going to multiply times the first element here. This row times the second column, so this is just times the first row. So notice, having a 1 in the first row and zeros here, 1 in the first row, first column, that's only multiplying by the first row, so that's not changing the first row at all. Same for the third. If we take the third row, we're going to multiply times the first column, so we get zeros, zeros, and a 3. 0, zeros, and a 3, zeros, zeros, and a 3. So if we only have a 1 here, then we're only multiplying the third row by 1 in each time. Remember, we do this row times this column, but each of these is being times 0. So that will yield that third row. So let's look at our second row. We're going to take this row times the first column, so we get twice the first row, plus the second row, so 2 is 4. Now, and then 0 and 3 is 0. When we do this times the second column, we're doing twice the first row, hence our operation, twice the first row, 1 of the second row. So 2 and 2 is 4, none of the third. Then this one times the third column, twice the first row, plus our second row, none of our third row. So whatever row we're wanting to change, that's the row that we're going to rewrite in our identity matrix to make it become our elementary matrix. And these coefficients tell us what we're going to do. We're going to double the first row. We're going to add the second row. So let's just make it do a couple examples. We can still use a 3 by 3. So we'll start with our identity matrix. So if we want our first row to be twice our previous first row, then we, in the first row, we change the first element to a 2. So when we multiply a new matrix by this, if I have this row in a column, then I'm multiplying that times the first, so I'm doubling the first, and then I'm not doing anything to the rest of them. So that will double our first row. If we want to take our third row and do a third of our third row, then we go to the third row and we do a third of the third element. So the third element in the third row is here, so we do a third of that. So whatever row we're changing, that's the row that we're changing in our identity matrix, and this tells us which piece that we're changing. We're letting the third piece have a coefficient of 1/3. So if we multiply that times our new matrix, the first row is not getting multiplied by anything, the second row is not getting multiplied by anything, but the third row is being multiplied by 1/3. I guess technically the first row is being multiplied by 0, so we have no first, none of the second, but a third of the third row. So we looked at doing adding two rows, multiplying one row by a coefficient. If we want to swap two rows, if we want to interchange, for example, the second and the third row, then we just swap the second and the third row here. The second row becomes the third row becomes the second row. Now let's illustrate real quickly why this works. If we were to take this, remember we have to multiply. We're going to make sure we multiply on the left side with the elementary matrix. So we take the previous matrix we used, and let's multiply these together. So we're going to do the first row times the first column. So we have a 1 times a 1, 0 and 0. Then the first row times the second column. So 1 times 1, 0 and 0, 1, 0, 0. So notice when we multiply this, we're only multiplying the first row. So we get whatever's in the first row, and that's true for each column that we multiply that by. Now when we multiply this one by the first column here, 0, 0, and 1, so we end up with whatever's in the third row. Multiply this one, 0, 0, 3, so we end up with whatever's in the third position. And when we multiply this times here, we get a 0, and a 3, so we get whatever's in the third position. When we multiply this one times the first column, we get a 0, a 2, and a 0, so 2. Second column, 0, 2, 0, 0, 2, 0. So this, when we multiply times each row, we only get what is in the second position. So since we do row and column, the second position in this column is the second row. So notice we just interchange the second and the third row. Alright, so that's an intro to what an elementary row operation is, and we mentioned that to multiply by our elementary matrices, we always put the elementary matrix on the left. And we'll use the notation E to represent that a matrix is an elementary matrix. Now, when we think about taking a matrix and putting it in row echelon form, then we perform multiple elementary operations. So the way we keep track with those is using a subscript. The first elementary operation would be E sub 1. The second elementary operation we do would be E sub 2, and so forth. So each elementary matrix is invertible, and to think about what its inverse is, let's look at an example. So if we want the inverse of interchanging two rows, let's look at the previous one where we interchanged the second and the third row. So if I took this matrix and I interchanged the second and the third row, then I would get that. Well, if I wanted to go from here to here, then notice we would just interchange the second and the third row again. So if I took the second and the third row and I interchanged them, that would get those back to where they are. So remember our elementary matrix for interchanging the second and the third row, we interchange the second and the third row on our identity matrix. So if that was our elementary matrix, then the inverse of that would be the same thing. Because to get the inverse of this, we're just going to swap the second and third rows again. Now, if we want the inverse of doubling a row, let's suppose that our new second row comes from taking our previous second row and doubling it. We can think about the inverse of doubling, or to undo doubling something, we would multiply that by 1/2. So if our elementary matrix, and let's just use a 2 by 2 this time. If our elementary matrix to do this operation is that I double the second row, then in the second row, that's what I'm changing, then I want a 2 for the second element. So if we want the inverse of that, it would be to do the opposite thing. Well, the opposite of doubling something is to multiply it by 1/2. So in that same position, I would change from a 2 to a 1/2. This multiplies in the second row the second element by 1/2. So that's the inverse of multiplying a row by a particular number. Now, as far as adding or subtracting rows together, let's go back to using a 3 by 3. So if I want my second row to be minus 2 times the first row plus the second row, so I'm basically taking my second row and subtracting twice my first row. So that elementary matrix, I'm doing this on the second row, so the first and the third row are unchanged, but on the second row, I do twice the first row, and I'm doing the opposite of that, plus whatever my second row was, and then doesn't have anything to do with the third row. If we want the inverse of that, the inverse of subtracting twice a row would be to add twice that row. So let's get this down. So the inverse operation would be to add twice my first row. Still going to combine that with the second row, but we're going to do positive 2 times the first row instead of negative 2. So the inverse of that matrix, that elementary matrix, we're still doing this to the second row, but instead of multiplying the first row by negative 2, we're multiplying it by positive 2. So let's go back and refresh. To interchange 2 rows, that elementary matrix and its inverse are the same, because if we flip 2 rows, then to get back to where we were, we flip those again. Same 2 rows. This multiplies a row by a particular number, so the opposite would be basically to divide it, so to multiply it by the reciprocal. And here, if you could think about it changing the order, instead of subtracting twice the row 1, then we would add twice of row 1, and that would be the inverse operation. So instead of subtracting twice the row 1, we're adding twice the row 1. So that's the inverse operation. Now, one thing that they're going to ask for us to do is to multiply or to write a matrix as a product of elementary matrices. So let's think about getting how we got the inverse of a matrix. And the way we first got it, the inverse of a matrix, is we made an augmented matrix, and we did multiple elementary operations on the left side until it became the identity, and then whatever we had on the right, once we had the identity on the left, was our inverse. So we had started with our matrix and our inverse, elementary operations to make the left side the identity. I keep on saying inverse. This is identity. A matrix and the identity of the same size. We do row operations to get the left side to be the identity, and what's on the right is our inverse. Now, that I'm going to write this. That doesn't necessarily mean that matrix A is equal to the identity. I guess we could put a line in the middle. So, to illustrate that we're going to do a row operation on this, remember our row operation goes on the left. So our first row operation, we could illustrate by doing that. Now usually it takes more than one row operation to change this into the identity, so let's take that and do another row operation. And remember, we do those on the left. So if we did more row operations or elementary operations, we're going to keep putting those on the left. So we would have, let's say we had 5 of those, we would have the last one and the next to last one, like such. And whatever we do to one side, we have to do to the other, keeping in mind that we do all of those on the left. So let's suppose that at this point, this is the identity, and that's the inverse. So if this is the identity now, so change that to where we have the identity on the left and a matrix on the right. So what's on the right is our inverse. So that means that our inverse comes from doing all of these multiplying all of these elementary row operations together times our identity, which when we multiply times the identity, it gives us whatever we have. So multiplying our elementary row operations together, our elementary matrices, that is our inverse. Now, if we want to write our matrix, not the inverse matrix, but our original matrix as a product of elementary matrices, let's look at how we would do that. So if we take this and we want to get A by itself, then we want to get rid of this. So we're going to do the inverse of that on both sides. When I multiply a matrix times its inverse, basically those cancel and give us the identity. So that would give us E4, E3, E2, E1. Then we do the inverse of that. on both sides and work our way down. And long story short, I won't show you the whole proof. It turns out that our matrix A comes from multiplying by the inverse of each elementary matrix like such. Now keep in mind that our inverse, these were in the opposite order. From left to right, they went down. Basically, this was the last row operation, next to last to that, and then this was our first operation. So let's work an example of that and see how that all plays out. So, for example, number 42 says, show that each matrix is invertible and write it as a product of elementary matrices. So, if we have the matrix 1, 2, 3, 4, if we want to show that that's invertible, let's find the inverse of this. So, we could make our augmented matrix. So we have a 1 in our pivot, so we need a 0 here. So our second row is going to come from doing -3 of our first row plus our second row. So our first row is not changing, but we're going to do -3 times our first row, add it to the second row to get the new second. -3 in this, let's see, that's -6 and 4, so -2. -3, 0. -3 in that, that's 0, plus that, so 1. So our second row comes from -3 times our first row, so I messed up here. -3 times this one plus that one. So -3 times our first row is -3 plus 0, so -3. -3 times this, that's 0 plus that, so 1. Now we want to get a 1 here, so we want our second row to be the opposite sign, and we want to divide that by 2 or multiply it by 1/2. So the first row is not changing. Now we're taking -1/2 times that. 0 times anything is 0. -2 times -1/2. -3 times -1/2, so +3/2. 1 times -1/2, so -1/2. Then the last thing to do, we need a 0 above our pivot. So our first row is going to be changing, and the way we're going to get it is we're going to do -2 times this one, so -2 R2s plus R1 will give us a 0. So our second row is not changing this time. But our first row, we're going to take negative twice the second one, so 0 plus 1. -2 times this, so -2 plus 2. -2 times this, so 3/2 times -2. It's -3 plus that. -2 times the second row, so -2 times -1/2, so that's 1 plus 0, so 1. So barring any arithmetic mistakes, this is our identity matrix. So we showed that this matrix has an inverse. So now they want to write our matrix as a product of elementary matrices. So we need the inverse of the first matrix, the inverse of the second elementary one. And let's see how many do we have. We have one elementary operation, two elementary operations, three elementary operations. So we do the inverse of the first one, the inverse of the second one, and the inverse of the third one, and when we multiply those together, that should give us our original matrix. So our first operation was this. So the inverse of this would be, instead of subtracting 3 times the first row, would be to add 3 times the first row, and this is going to become our second row. So in our second row, we do positive 3 times our first row, and then our second row. The first row is unchanged. Here, our second row is what's changing, so the first one is unchanged. And in the second row, we're taking our second position and multiplying it by -1/2. The inverse of that would be to multiply it by a negative. To get back to the other sign, we need a negative. And the inverse of multiplying by 1/2 is to multiply by 2. And then this one is our first row that's changing, so our second row stays unchanged. And we subtracted 2 times our second row, so the inverse would be to add 2 times our second row, so positive 2 times the second row in our first row. So what we wrote were the inverse of these operations. So A should be the inverse of the first one, so 1031, times the inverse of the second one. This is the second one, so the inverse was this, 100, -2, times the inverse of the third. This is the third operation. This is the inverse of that. Now, if we were to multiply those out, we should end up with the matrix we started with. So if we want to check to see if this is correct, to multiply these out, let's just multiply the first two together. So we're going to do row times column, so 1 plus 0. Row times the second column, so 1 times 0 is 0, 0, so 0 plus 0 is 0. Second row, first column, so 3 plus 0. Second row, second column, so 0 minus 2. So that's that product. Let's multiply that times the last matrix. So the first row, first column, so 1 plus 0. First row, second column, so 2 plus 0. Second row, first column, so 3 plus 0. Second row, second column, so 6 minus 2 is 4. And if we scroll back up, that is the matrix we started with, 1, 2, 3, 4. So our matrix came from doing the inverse of each elementary row operation and multiplying those in that order. If we were to take just the regular operations, keep in mind that we've seen in the past, if we raise each of those to the -1, that becomes a to the -1. This inverts each of these, but it also changes the order. So this one comes over here. So that's the inverse of this. Well, the inverse of an inverse is that operation. Then this one, basically -1 and -1 cancel. And then this one. -1 and -1 cancel. So remember, we have a product of matrices raised to the -1. We flop the order, and then do the inverse of each. Well, the inverse of each of these are these matrices. So that's, once you remember, okay, one of these, the order of one of these, then you can get the other one by doing the inverse of both sides. Now the last thing that we're going to do in this section is to write the square matrix as a product of elementary matrices and an upper triangular matrix. So when we say that something is upper triangular, I guess I'll read the definition out of the book to start with. It's a square matrix that all the components below the main diagonal are 0. So if this is our main diagonal, all the components below that are 0. Now we can have any number we want to up here. And sometimes the numbers on the main diagonal are 0. Notice this number here, this is on the main diagonal, but it's 0. So everything below the diagonal has to be a 0. We could have zeros other places, but everything below the diagonal has to be a 0. So this is upper triangular. That's upper triangular, because everything on the lower side is 0, everything on the lower side is 0. A lower triangular matrix is just the opposite. Everything on the lower side, or opposite of the lower side, are 0s. So if we had those, then everything above the diagonal is 0s. So this is lower triangular, because if we have numbers, it's in the lower triangle. This is upper triangle, because if we have numbers, everything in the upper, the numbers are in the upper triangle. So they give us some problems, and they say to take these matrices and write them as a product of elementary matrices and an upper triangular matrix. So let's take the matrix 2, -3, -4, 6. So that's A. So basically what we're going to do is we're going to take this matrix and we're going to put it in row echelon form so that we get 1s on the diagonals, 0s below it. And once we get that, we're not going to put it in reduced row echelon. We're not going to worry about having 0s here, just 0s here and 1s here. So let's begin by making our first row half of what our first row was. So we do half of that, we get a 1, half of that, -3/2. And then if we want a 0 here, then our second row, we're going to take, we need a 4 here, so we do 4 times our first row and add it to our second row. So our first row is unchanged, but our second row, we're doing 4 times this, so 4 minus 4 is 0. 4 times this, so -3/2 times 4, so that -6, plus that, so 0. Notice at this point, that's upper triangular, because everything below the diagonal is 0. So let's write this matrix as a product of elementary row operations and this upper. All right, now let's quickly go back and look at what we did. Started out with matrix A, and we multiply that times a row operation. We did a row operation on it. We did that another row operation on it. So we did 1, 2 row operations on A. And what that gave us was our upper. So after doing the first row operation, and then the second row operation on A, remember we do when we illustrate it as elementary matrix, we multiply A on the left. So we multiply A on the left by the first one, and then our result on the left by the second one. And our result was our upper. So they want us to write A as a product of elementary matrices in the upper. So if we solve this for A, we need to get rid of this. So we want to multiply that by the inverse. So we have to do that on both sides. Now those will undo each other, so that gives us this. And then to get A, we need to multiply by the inverse of this one on both sides. So those undo each other. So A will be the inverse of the first operation, the inverse of the second operation times our upper. And that will be true no matter how many of those we have. So let's go back and see what these are. So if this is our first operation, the inverse of that, the inverse of multiplying by 1/2 is to multiply by 2. We're doing that on our first row, so doing twice our first row. The second row is unchanged. And then our second operation is affected on the second row, so the first row stays the same. The second row, the opposite of adding 4 would be to subtract 4. And we're doing that on the first and our second. So this is the inverse of the first elementary operation. This is the inverse of the second operation. So our A should be the product of that one, 2001, times the inverse of the second operation, 10, -41, times the upper. And the upper was this, 1, -3/2, 0, 0. So let's see if that works. We can multiply these two together and then times that, or these two and then times that. Doesn't necessarily matter. So let's see if we did this correctly. It's Monday morning when I'm making this, so I could be wrong. Wouldn't be the first time. So we multiply these together. We do this row times this column, so 1 and 0. This row times that column, so -3/2 and 0. This row times the first column, so -4 and 0. This row times this column, so negative times negative is positive. 4 times 3/2, I believe that's 6. And then multiply these together. This row times this column, so 2 and 0. This row times this column, so that's -3. This row times this column, so 0 and -4. This row and this column, so 0 and 6. And if we go back up, 2, -3, -4, 6 was our A. So we did get that correct after all. So the trick on all of these, whether it's rewriting a matrix as a product of elementary operations, or whether it's writing it as a product of elementary operations and the upper triangular, is to remember, okay, is our result, does it involve inverse elementary operations or our elementary operations? So a good way to remember that is, well, what did we do when we were starting with A? We multiplied it by an inverse or an elementary row operation, and then another one. So if we want to get rid of those, like so forth.